Well, we're going to start a new unit today. It's going to be topic 3, which is about the chemistry of biology. Anyway, some of this should be pretty much review for what you had last year in chemistry. We discussed how the basic unit of matter is the atom. Same thing in biology here. And we also discussed how atoms can be split apart into 3 subatomic particles, and depending on how those particles come together, it forms a different type of element that's on the periodic table. And what we'll just find out in the next lecture is how these elements come together to form organic macromolecules, which are necessary for biology to take place. So let's go ahead and just look at the subatomic structure. Well, the 3 subatomic particles, as you probably know, are neutrons, protons, and electrons. And I've gone ahead and abbreviated them here, as you can see. I should probably use a different color besides red, because that's one that's already in there. Let's try that. As neutrons with an N, P for proton, and E for electron. Now they have 2 different properties which give them the ability to do what they do, and those 2 properties are their masses and their charges. So let's talk about mass first of all. So the mass of a single neutron is 1. The mass of a proton is 1, and the mass of an electron is actually 0. Now that kind of throws some people. 0, how can something have a mass of 0? It wouldn't really be mass. Wouldn't really be matter. Well, it does actually have a mass. It's very, very small. It's 0.000 something like that. But for our purposes, let's consider it just to have a 0 mass. Okay, so the nice thing about these numbers, though, 1, 1, and 0, is that therefore the mass of something would be the same as the number of something. So if I had 5 neutrons, I could also say that it has a mass of 5, because each one is 1. Pretty simple, right? The second property that is important here is charge. Neutrons got their name because they're neutral. They just don't have a charge. But protons and electrons are positive and negative, so proton pro for positive. That has a charge of +1, and electrons have a charge of -1. So again, we see zeros and ones. That kind of makes it easy to make a connection between the number of particles and the charges on them. Okay, now let's put this information together into some laws that help us to figure out why atoms are different. So here's what I call the element rules. So let's take a look at rule number 1. How do we figure out the mass of an atom? Well, the mass would be the sum of the particles. And again, since the masses are 1 and 0, it would simply be the sum of the number of particles. So if I add up the number of neutrons plus the number of protons plus the number of electrons, I should get the mass of that atom. But I just told you that electrons, right, don't have any mass. So therefore, we could say that the mass really equals the number of protons plus the number of neutrons. That's our first rule. Now here's our second rule concerning those charges. The net charge on any atom has to be 0, or it just doesn't exist. It falls apart. Now, we learned last year that we could have ions which could be charged, but atoms have to be neutral 0. Now, since neutrons have no charge on them, they're not going to affect that equation. The protons and electrons would affect it. But since they're positive and negative, yin and yang, up and down, the number of protons would have to equal the number of electrons for the charge to be neutral. So those are always going to be the same. And the third rule here is that it is actually the number of protons which defines what element we're talking about. So if I look on the periodic table and I look up element 6, which happens to be carbon, the reason why it's carbon is because the number of protons is 6. If it had a different number of protons, if it had 7, it wouldn't be carbon anymore. It'd be the next element. It would be nitrogen. Okay, let's go ahead and put these rules together here and see if we can do some calculations here. So let's go ahead and try calcium, for example. So I'm going to go ahead to the internet for a moment here, and let's bring up a periodic table, shall we? Let's see. There we go, periodic table. And let's just use calcium as our example here. So tons of periodic tables here. Well, let's take a look at this one, see what we get. Awesome. There's calcium down here at 20. Let's go ahead and click on that. Now you see that calcium is element 20. That means it must have had 20 protons. Very good. But you also see that the weight of calcium is 40.08. Now don't worry about the 0.08. We'll just round it and keep it simple for now. So let's suppose that the weight is 40. Now let's go back here and do a calculation. So calcium, right, is element number 20. Very good. Now what does that mean? It means that the number of protons is 20. Now if the number of protons is 20, it must mean that the number of electrons is 20. That's the second rule. The charge has to be equal. Now what about the weight there? Now the weight, according to the periodic table, was 40. Okay? So let's go ahead and do it. Weight equals protons plus neutrons. If I know that the weight is 40, and I know that the number of protons is 20, therefore the number of neutrons must also have been 20. Okay? Now let's put that in there just so you remember what I'm talking about. Okay? Very, very simple. So the number of neutrons in calcium had to be 20. Now it didn't have to be that way, right? Let's go ahead and do another example. That one came out a little too clean. It doesn't always have to be the same numbers. How about zircon? Let's try that one. Now zircon is element 40 and it has a weight of 91. So let's go ahead and take a look at zircon. So zircon is element number 40, so that means it has 40 protons. That means it had to have 40 electrons. And the weight, we said, was 91. Well, the weight, which is 91, has to equal the number of protons plus the number of neutrons. So in this case, zirconium must have had 51 neutrons. Pretty simple how we do that, right? Okay, let's go ahead and look at one more thing here. Not all electrons are created equal. Now, last year you learned that electrons are not just randomly distributed around an atom. They're actually distributed in rings. And there's an exact number of electrons that can go into each rings. The electrons which are in the outermost ring are the special ones. They're called the valence electrons. Why are they special? Because those guys can go ahead and react with somebody else. So that was the most important thing. They form bonds. So we need to know how many valence electrons, and we can do that by, again, looking at the periodic table. So let's look at calcium, for example. Calcium, we already said, was element number 20. There it is right there. Now you'll notice that it's in row number 4. Row number 4 means that the electrons are distributed in 4 rings around the nucleus of calcium. How many valence electrons? Well, if you look in the column, that tells you the number of valence electrons, and we see the number 2 there, which means of the 20 electrons in calcium, you distribute them in the 4 rings, and 2 of them end up in the final ring number 4, and those guys are the valence electrons. Okay, that's a pretty good reminder of what we did last year. We're going to go ahead and do a little worksheet now to just make sure that we understand these ideas.